Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and would also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today I've got something completely different for you. Today, we will go through our very first Python tutorial on algorithmic trading using cointegration and statistical arbitrage. We had already got a video on cointegration and pair trading in Excel, so please check this out if you're interested in the theory behind it, but there were many requests from you to do a more rigorous and robust version of it in Python applications as well. So today is what we will do. We will code our own trading bot that will use cointegration using a pair of stocks and undertake trading decisions, and we'll see how well this strategy performs in real time. So first of all, I'll teach you how to get Yahoo Finance installed so that you can use the Yahoo Finance API to parse data and get stock prices and much more straight into your Python environment. To do that, we're going to go to the Anaconda PowerShell prompt, which would be just the command line, but operating within the Python environment. And here we can pip install the Yahoo Finance package, which is called yfinance. And as we press enter, the environment will check whether we have got the package already installed, and in my case that's the case because the requirement is already satisfied. If you haven't got it installed yet, there will be a quick download process, and as soon as the default command line appears at the bottom, you're ready to close it and proceed to the code itself. So first of all, let's import the packages we'll need for our trading bot, and obviously we cannot do without our standard NumPy and pandas for arrays and data frames respectively. Then we need the Yahoo Finance itself, yfinance, and let's import it as yf for brevity. Then we also need the stats models API package for a linear regression model to get our cointegration, our unit root regression down the line, and we'll import it as sm for brevity as well. Then we'll need the package scipy.optimize, and we'll import it as pop, just to optimize the parameters of our cointegrating equation so that we have got our dynamic equilibrium satisfied with the highest probability possible to make our relationship that we trade on the most robust we can make it. And also for visualization, let's import matplotlib pyplot as PLT to get some equity curves and nice graphs down the line as well. So importing these packages, we can proceed to specifying the major parameters of our trading bot. So first of all, let's specify what is the pair we will trade on. And I was not planning to be too fancy with it. Let's just go for a pair of established US financial stocks. So we go JP Morgan, JPM, and Citigroup, C. So you just input an array, a list of tickers from Yahoo Finance, and then Yahoo Finance will be able to retrieve the price data for these stocks. Then we'll need to specify what is the start and the end date for our strategy, and let's start at year-end 2019, so 31st of December, and here you need to input dates as string variables in American date format, and let's end today, 2021, March 8th. Then we can specify the further parameters of our strategy. So let's input what is the trading fee, the brokerage fee we need to pay to our broker to facilitate our trades. And regular, quite typical fee would be 0.1%, so 0.001. We'll also need to specify what is the rolling window of our parameter estimation, so how far back will we look to estimate our cointegration equation and trade based on it. So let's specify that the length of our window is just 1 year, 252 trading days. It would mean that we'll estimate our first model at year-end 2020, 252 trading days since this start date, and then we'll have full 2 months plus a little bit extra to trade based on constantly updating co-integrating models. So that's quite nice that our model will be updated every single day to incorporate the most recent, the most relevant data into the equation. And then we need to input the threshold value of the t-statistic that we consider reliable to trade upon. The t-statistic will be retrieved from our unit root regression, and it's generally postulated that the lower it is, the more negative it is, the better. And the usual rule of thumb in unit root tests is that your t-statistic should be less than minus 2.5. So minus 3 is very good, minus 4 is excellent, minus 5 is wonderful, and so on and so forth. So let's specify that our threshold value of the t-statistic is minus 2.5. If it is less than that, then we trade. If it's more than that, we don't. That incorporates some reliability, some tolerance band for our strategy, so we would not trade on pairs that are not co-integrated. That out of the way, we can proceed to retrieving our data from Yahoo Finance. To get that, we'll just initialize two empty data frames for prices, let's call it just data. So initializing an empty data frame data and an empty data frame returns, which would be also inputted using the PD function. And then for stock in stocks, so for every single stock from our stock array, and here we have got the simple case of two stocks, but in later tutorials we'll generalize our strategy for all potential pairs of a wider range of stocks, we'll retrieve prices using the Yahoo Finance download function referring to stock sticker, so stock from stocks, the start date and the end date. That's all we need. Then, to just refer to the closing prices, that's what we need. We will estimate our strategy on every single day's closing prices and make respective decisions. We'll get data stock, which is basically prices of a respective stock, as the closing values from the prices data frame we just retrieved from Yahoo Finance API. And then the returns of each and every stock would be calculated based on the respective closing prices. And here we need to, first of all, make sure that the returns are calculated properly, day to day, and second, that the length of our return data frame is the same as the length of our stock data frame. Naturally, if you calculate returns from 100 prices, you'll have 99 returns. So to make the lengths of arrays comparable, we need to provide for that. So first of all, let's calculate returns based on closing prices. So first of all, we can refer to data stock 1 colon nothing, which would mean that we'll take price values from the second day. Well, it starts numerating from 0, so 1 would be the second day until the very end. And we need to reset index drop true so that pandas stops referring to our data points according to their indices, so we have a proper division here to calculate the returns. And then we need to divide it by lagged stock prices from the very beginning until the penultimate stock price. So until -1, so until the last non-inclusive. That's how this command works in pandas to refer to various slices of arrays and series. That's the same way it works in NumPy as well. And now we can subtract 1 to get returns and not capital growth rates, and to make both series of the same length, we can use NumPy append and append 0 to the array of returns. That would mean that on the very last day, when we only know the closing price, we have no information on what the return would be, so we would just assume it is equal to 0, so we cannot make any reasonable trading decision based on that. And now we have completed the procedure of downloading our data and calculating prices and returns. So here we can see that the Yahoo Finance interface tells us that both tasks are completed. We can see whether our data frames for stock prices and returns work well. So referring to data, we can see those are dollar values of stock prices for JP Morgan and Citigroup at every single trading day from year-end 2019 until last Friday, 5th of March 2021. It hasn't reported the closing price for 8th of March yet, as the markets are still open as for now. So that's what we would have expected. And then if we return the returns data frame, we have got percentage returns indexed according to the number of the trading day, and the very last but the very last observation is zeros as we actually wanted. So that's all nice and fine. Now we can proceed to our cointegration strategy logic to figure out what is the optimal pair trading signal, what should we short, and what should we long, if any. So we start by initializing our arrays that would characterize how our strategy performs overall. That would be the array of gross returns, which would be just an empty numpy array to start with. And we also need an empty array of net returns initialized. Also, just for the reporting purposes, we'll get an empty numpy array of optimal t-statistics that we will have calculated from our cointegrating equation to see whether the pairs is becoming more or less cointegrated throughout our trading period. Now we can specify that our first stock is stock 0, so 0th element from our stock array over here, from our stock list, JP Morgan and Citigroup, and stock 2 is stock 1. So that would mean that stock 1 is JP Morgan and stock 2 is Citigroup. Now we can finally start moving through our sample in a loop for t, which is just the time indicator, in range, starting from our window. So this is the first day we can trade based on our rolling window model estimation. So from window until len data, basically until the last observation in our sample non-inclusive, meaning that we would not have our final observation included into the calculations, which is something that we want given the fact that we don't know the return yet for our very last day in the sample. Now we can define our unit root function that we'll use as the centerpiece of our cointegrating pair trading statistical arbitrage strategy. So we can just define the strategy, define the function called unit root, which would have only a parameter b as its argument. As we have already mentioned in the previous tutorial in Excel, we can only specify our long-run equilibrium relationship between two stock prices, just referring to the parameter b, and the parameter a can be calculated to satisfy the unbiasedness criterion for the equilibrium relationship. What it means: imagine that we have chosen some parameter b that characterizes the relationship between the prices of stock 2 and stock 1. Then a can be calculated to make the forecast unbiased by just calculating the average of stock 2 minus b times stock 1. And that's what we'll do straight away. We'll calculate our a as numpy average of stock 2 prices. So basically, those would be data stock 2, which is prices of stock 2, for our whole rolling window, meaning that we will end certainly at day t, and we will start at day t minus window, meaning that we'll go through 252 trading days that we'll use to estimate our cointegrating equation. And then we need to subtract b times the same reference for stock 1. Having calculated our a parameter, we can calculate fair values of stock 2 based on prices of stock 1 and the values of parameters a and b we have presumed. That would just be a plus b times the respective values of stock 1 prices that can be copied from over here. Nice and easy. And then we can calculate the deviations of the fair value from the price. And that could allow us to extrapolate trading signals based on whether stock 2 in our pair is overvalued or undervalued with respect to stock 1. So the difference, the deviation from the fair value, would just be the array of fair values minus the data stock 2 from t minus window up to t. And then to estimate how convergent this long-run equilibrium is based on the assumed value of b and calculated value of a, we need to calculate the differences in difference, so the dynamics of this deviation from equilibrium. We want it to converge to 0 in the long run for us to profit from our statistical arbitrage trade, and we can just subtract from the differences in day 2 up until the very end, the lagged differences from the start until the penultimate observation. And then we can regress the difference in difference onto the lag difference to get our unit root test down the line. That would allow us to calculate the Dickey-Fuller t-stat and compare it to our threshold and optimize it by varying the parameter b to get the most convergent, the most reliably convergent relationship we could get on this particular pair. To do that, we have to use the stats models instruments. So basically we'll code our linear regression reg as OLS regression from stats models package, and as our y variable we'll get difference in difference we have just calculated, and as our x variable will include lagged differences from the start until the very end, apart from the last observation. And we don't need to include the constant here, as it's a simple no constant, no trend unit root test. We want this dynamic equilibrium relationship to be quite stable over time, without any drift, without any trend, for us to be able to get our trading signals easily from the parameters we have estimated. And now we can get the result of our regression equation, the parameters, the coefficients, everything we need, by fitting our regression model we have just specified. And having calculated the parameters and the standard errors in this res variable, we can return the output of the unit root function. And the output of the unit root function would be just the Dickey-Fuller t-stat, which would be the first coefficient of our regression model. Well, the only coefficient, that is, because we haven't got a constant or anything else. But here, as res params is the array of coefficients, we can refer to the 0th value in it to get the very first coefficient as a number, as a float, and divide it by the respective standard error, which would be included in the array BSE. B stands for estimators, well, B0, B1, B2, and so on and so forth, and SE stands for standard error, so quite intuitive in that regard. And we can also refer to the 0th one, which corresponds to the standard error of the 0th, the first coefficient in our model, and that in all will return the Dickey-Fuller t-stat. And now we need to vary the b parameter in our cointegrating equation that specifies the dynamic equilibrium we can trade upon. We can vary this parameter b to minimize our t-stat, to make it as negative as humanly possible. And this is where the scipy.optimize package comes in handy. We can specify the optimization result as a variable res1 and refer to spop minimize function, accounting for the function we want to minimize by varying its input variables, the starting value of such variables, and the optimization algorithm, which numerical method you want to use. And that's actually quite similar to the solver instrument in Excel. However, here you can apply it many times in sequence and apply it much more flexibly. That's where Python's scipy.optimize shines, really. So the function we want to minimize is the unit root, the t-stat that is returned from this function we have just coded. The starting value can be anything, really, simply because this function is smooth and is a function of only one variable, so it will reasonably converge no matter what you include as the starting value. But to make life easier for scipy.optimize and to make our algorithm faster, let's include some value that is theoretically close to the true value of b. And here, as we might assume a can be equal to 0 in our starting iteration, the value of b would just be the price of stock 2 over the price of stock 1. So let's input that as our starting b value. So data stock 2t over data stock 1t. That's the starting value of our parameter b, and then the system, the numerical algorithm, will converge to the optimal value by changing the b parameter starting from this value. Then we need to specify our method, and here the two default roughly equivalent methods for such a simple task would be Nelder, Mead, and Powell. Nelder, Mead performs faster in case of simple, smooth functions. Powell can perform better when the function is more complicated, and it is a little bit slower. Here, as the as the function is quite simple, let's stick with Nelder, Mead as our method. And now, having minimized our t-stat, having obtained the optimal t-stat, the minimum possible value that signifies the most robust, the most convergent dynamic equilibrium we can trade upon, let's retrieve our parameters and our t-stat. So our optimal t-stat, t-opt, would be the value of the function we have obtained by minimizing our res1 task. So res1.fun, that's the attribute of the res1 variable, that's the value of the function that is minimal, we have achieved. And then the optimal value of the parameter b that we will use in our trading will be the optimal value of the x variable, the independent variable we vary to obtain this minimal function value. So that can be retrieved by using res1x, but given the fact that by default x can be an array, so it can be a function of multiple variables, we can refer to it as float res1x, so that Python interprets it as a float number. Now, using the same logic we did here, we can calculate the optimal value of a, and we can just copy that across and substitute b here by b_opt. That is the new value we have actually obtained from our optimization task. And now we can finally calculate the fair value of stock 2 at time t. And that would be a optimal plus b optimal times data stock 1 t. And that actually gives us an idea of whether stock 2 is over or undervalued at this particular day, and can give us some advice already into whether long it or short it. Now we can already start simulating our trading, and that involves considering a range of various possibilities. So first of all, to calculate our trading fees, we need to know where we were at before, so what was our portfolio at time t-1, and what our portfolio is, what our signals are at time t, and then based on the changes in our investments, we can calculate our trading fees. However, at the very start, we need to implement the fact that we were sitting in cash. We had no investments at the start of our observation period. So if t is equal to window, so that's if that's the very first day we started trading, the old signal is 0, meaning that we haven't traded before and we're sitting in cash, and that would be used to calculate our trading fees at the very start of our period. Then we need to acknowledge the fact that our optimal value of t can be greater than our threshold, so our cointegrating relationship can be less convergent, less reliable than we want. So if that's indeed the case, if t optimal is greater than t threshold, then we need to say that our signal is 0. We do not trade on that pair, we just sit in cash, simply because we cannot rely on such a noisy cointegrating equation, on such a noisy dynamic equilibrium relationship. And as we're sitting in cash, our gross return is obviously 0 at that case. Then, if it's not the case, if our cointegrating equation is reliable enough for us to trade on it, then else the signal of our trade at that particular day would be just the sign of the difference between the fair value and the price of stock 2. If this is positive, it means that stock 2 is undervalued and we need to long it and short stock 1, which is overvalued with regards to stock 2, and vice versa. If this difference is negative, it means that stock 2 is overvalued in terms of its fair value, so we need to short stock 2 and long stock 1 instead. So now we can actually implement this logic in terms of the gross return calculations. So the gross return, in that case, if we do trade, would be the signal times the return of stock 2 at day t minus the signal times the returns of stock 1 at day t. And that would mean that we are longing stock 2 if we have a positive signal here and shorting it otherwise and doing the reverse for stock 1. That would capture all possibilities for our trading signal and for our trading procedures at every single day of our strategy's lifetime. Now we can calculate the trading fees, and we already move out of this cycle because calculation of fees is exactly the same no matter what. Our fees would be equal to the level of fees we pay to our broker, 0.1% in our example, times the absolute value of our signal minus the old value of the signal. So it means that if we stick with the same strategy, we do not have to buy or sell anything, so our fees are 0. If we were sitting in cash and we proceed to longing or shorting one or the other, we need to pay fees once. But if we proceed from longing to shorting or from shorting to longing, we need to pay double the fees because we have to close old positions and open new ones. That accommodates for varying level of fees in this simple pair trading strategy. Then obviously we can calculate net return by just subtracting the fees we have just calculated from the gross return. And we can append our return arrays with relevant variables. So we do it for gross returns and we do it for net returns as well by just changing the respective variable names. And then we need to append our t's array with our optimal value of the t's that we have calculated for this particular day. And now we can already report the results day to day, so we can see what's going on at every single trading day with our strategy, whether I'm making money, whether we're losing money, and we'll just build up some quite intuitive and simple interface to provide for that. And at the end, we'll plot the equity curves that would characterize our strategy's performance, both gross and net. So here, let's say that we first print what trading day we are investigating. So day plus the string variable of data index t, which would just print what day we're currently at. Then we'll print an empty row for so that the interface is not cluttered. And then if signal is equal to 0, we print that there is no trading going on that particular day. Elif, so it means else if signal is equal to 1, we can print that we are actually opening a long position on stock 2 and a short position on stock 1, corresponding to this logic of the fair value we have implemented. So we print a long position on stock 2 and short position on stock 1. And else, and the only other scenario we need to consider is when the signal is equal to -1, then it's just the reverse. We open a long position on stock 1 and a short position on stock 2. And then we can, regardless of what's going on with our trading, refer to our gross and net returns. So gross daily return would be equal, well, here we can report it in percentages and round it, so it is nice and readable. So we need to report the string variable of the rounded value of our gross return times 100, so we report it in percentages, rounded to 2 decimal points, and then we need to add a percentage sign. Then we can do exactly the same for our net daily return. Here we can just change it in text and change it here in the variable name. And we can also print what is the cumulative net return so far. So cumulative net return so far. Here we would just need to refer to the numpy prod of 1 plus net returns times 100 minus 100. So we get returns and not growth rates. Here we have got everything we actually needed in terms of the interface. So we print an empty row, and then to calculate the fees for the next day, we say that old signal that we'll refer to in the next day is equal to the current signal. And finally, when we have calculated it for all of our trading days, we can plot our equity curves. So we'll plot the NumPy cumulative products, cumprod, of 1 plus gross returns. And then to start at 1, we can use NumPy append 1 and that. And also plot the equity curve for net returns as well. And that's all we need for the code. We can run it and see that it starts calculating it day to day and reporting the intermediate values at every single day. We can see that at first our cointegrating equation was not reliable enough for us to trade on it, and it remains the case until 12th of January 2021, where we start opening a long position on JP Morgan and a short position on Citigroup, losing a little bit and paying the fees, so our net return is minus 0.29%. Then we make a bunch more losses. However, here we stay in the same position, long in JP Morgan, short in Citigroup, so we do not pay any fees, so our gross return in that day is equal to our net return in that day. Then we make a lot in the single day, recovering all of the losses we've made so far. So here our cointegrating equation actually paid off. We have arbitraged successfully based on our statistical arbitraging technique, and we proceed to doing the reverse, long in Citigroup and short in JP Morgan. Here we were banking on the relationship reversing, and it did indeed reverse. So here we expect it to flip the other way in the next couple of trading days. And we see that we do make these decisions every single day. The code reports what we do, the code calculates the fees that we need to pay, and at the very end, it reports the overall equity curve. We see that at first we were not trading, then we lost a little bit of money, and then we started making money quite consistently, and at the very end, our cumulative net return was excess of 4% net of fees, which is 4% in slightly more than 2 months, which is nothing to be ashamed of. That's quite a decent return one can obtain realistically on such a market while not backtracking any of your decisions and only making your decisions based on signals you retrieve from prices you know so far. And obviously, there is a lot of room for improvement of this particular trading strategy, of this particular algorithm. You can include more potential pairs and select only the most tightly cointegrated pairs at every single day and see how it changes the results. Or you could also weigh various pairs according to the tightness of their cointegration relationship. And that's what we'll do in our next tutorials on cointegrating strategies in Python. Please leave a like on this video if you found it helpful and you enjoyed the format of Python tutorials. In the comments below, I'm eager to see any further suggestions on videos for business, economics, or finance topics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.